In the last lecture, we discussed the exchange interaction and showed how this interaction is responsible for magnetic ordering of spins in a ferromagnet. In particular, we pointed out that this exchange interaction has the form due to Dirac and Heisenberg. It is known as a spin Hamiltonian because this interaction energy is written in terms of spin operators only, and it has the form minus 2Jij Si dot Sj, and we will just write J. So, if J is greater than 0, that is, if the exchange integral J if J is positive, then the ferromagnetic ground state is energetically favored. So, it becomes the ferromagnetic alignment means that the two spins I and J are lined up parallel. So, the two spin wave function has the form of parallel spins, or it can also be like this, both up or both down, or it can be a symmetric linear combination of this So, all these three spin states, spin combinations are energetically degenerate. So, this is known as a triplet, whereas the excited state will be an antiferromagnetic excited state, which has the form which is an antisymmetric combination. All these have S equal to 1 and this has S equal to 0. So, you have a ground state which is triplet and an excited state. This is the situation, this is antiferromagnetic, this is the ferromagnetic. So, this is the situation for J greater than 0. We also said that it will be reversed and the triplet will lie higher while the singlet lies lower if it is an antiferromagnetic ground state for J less than 0. If the exchange integral is negative, this is what will happen. So, this will have S equal to 1 and this will have S equal to 0. So, this is what we discussed last time, and so we have both ferromagnetic and antiferromagnetic ground states are possible depending on whether the exchange integral J is positive or negative. Therefore, what happens in a real crystal consisting of a very large number of spins, all the spins will be lined up parallel, then it becomes a ferromagnet, and all the spins are anti-parallel in pairs, then it becomes a antiferromagnet. So, these are the different ways of magnetic ordering, spin ordering. But in the case of an antiferromagnet, since you have half the number of spins lined up in one direction and the other half lined up in the other with equal and opposite moments, the magnetization due to one sublattice cancels completely the sublattice magnetization due to the other. Therefore, the net magnetization of an antiferromagnet will be 0. So, if you measure the magnetization, it will not be clear whether it is an antiferromagnet or it is a non-magnetic material. So, what is the best way to detect antiferromagnetic ordering? So, there must be an experimental method to distinguish an antiferromagnetic material from a non-magnetic material, because both have 0 magnetization. So, the antiferromagnet becomes antiferromagnetic below the Néel temperature. So, we also would like to know what is the Néel temperature. So, the best way is to carry out the experiment called neutron diffraction. If one performs neutron diffraction above and below the Néel temperature, this is the Néel temperature at which the material becomes antiferromagnetically ordered. So, if you carry out neutron diffraction measurements both above and below the Néel temperature, then it is possible to say whether a material is an antiferromagnet or not. This is because neutrons have a magnetic moment, even though they are electrically neutral particles, but still they carry a magnetic moment. Because they have a magnetic moment, the neutrons can interact with the spin magnetic moments of the ordered spins in the crystal lattice. Therefore, because of this interaction, they can be diffracted just like X-rays get diffracted by atoms in the crystal lattice. Only thing is, the interaction here is magnetic, whereas in the case of the conventional X-rays, the electromagnetic waves interact with the charge clouds of the electrons in the material. So, the neutron diffraction intensities will be determined by the nature of the ordering of the spins, which differ substantially from the atomic or molecular ordering, because the atomic or molecular ordering comes because of the periodicities in the electron charge distribution, whereas here the ordering neutron diffraction intensities arise from the periodicities in the magnetically ordered spin configuration. So, the magnetic ordered lattice may not be the same as the crystallographic lattice. Therefore, the diffraction intensities can be substantially different from that of the X-ray diffraction intensities. So, that is why by performing neutron diffraction we can detect spin ordering. Antiferromagnetic crystals provide the most striking neutron diffraction patterns. That is because the sites occupied by the magnetic ions in these materials are all crystallographically equivalent. So, they cannot be distinguished crystallographically, but as the crystal is cooled through the Néel point, extra lines appear in the neutron diffraction pattern because of the ordering into magnetic sublattices introduces additional periodicities in the lattice which were not present before above the Néel point. So, the magnetic periodicity give rise to what are known as superlattice lines. Due to magnetic ordering. So, the appearance of the superlattice lines below the Néel temperature is due to the magnetic scattering of the neutrons when their magnetic moments interact with the magnetic moments of the ions. Examples of such abound in nature, such materials, but a simple example is for a crystal shown in the next figure. Here you have the Bragg diffraction from a magnetically ordered solid. This lattice is a body centered lattice, and if there are no magnetic moments on the ions, there are two different layers in this figure, the A plane ions, and they cause constructive interference and they interfere with the wave fronts from the neighboring B planes with the neighboring A planes, but there would be also destructive interference from the wave fronts from the neighboring B planes, which are through the body center. Because of that, no Bragg reflection would normally occur because of this cancellation. But if the ions are magnetic ions, then what happens is the amplitude of the wave reflected from the A ions plane will differ substantially from that of the plane of the B ions because of the additional magnetic scattering contributions. They depend on the angle between the moments, the spin moments of the ion and the incoming neutron beam. So, the destructive interference will then be incomplete, and therefore, you get a diffraction line at that particular angle. Whereas, if even though the ions are magnetic, but if we are above Néel temperature where there is no order, then they will not give this extra line. Therefore, one can distinguish easily the onset of magnetic ordering, antiferromagnetic ordering in particular, at the Néel temperature by the appearance of these magnetic superlattice lines. The positions of the superlattice line are indexed just the way the X-ray diffraction lines are indexed according to the plane from which they are reflected, and that is the position. Then the next information is their relative intensities, which tells us about the nature, the kind of ordering pattern present. Then you have also the Néel temperature. One can determine the temperature at which these extra lattice superlattice lines occur, and this will give an indication of the Néel temperature. Next figure, for example, shows a typical case of magnetic structure of a compound called manganese fluoride, MnF2, where such a situation exists where the ions occupy both the corners of the basic cubic cell, unit cell, as well as the body center, and therefore, there will be extra superlattice lines at the Néel temperature. So, there will be, this clearly shows that there are the body centered, the ions occupying the body corners and the ions occupying the body center, they are anti-parallel. Therefore, there is an antiferromagnetic alignment, and this causes a non-zero Bragg reflection from the 100 plane. So, this extra line, which is not normally present in the above Néel temperature, will start appearing below the Néel temperature. So, one can determine the Néel temperature also in this way. Next figure shows the similar situation in the oxide material, manganese oxide, where you have ordering above and below Tn in a similar fashion. In this case, of course, the magnetic reflections are from the 111 planes, indicating that corresponding ions on successive 111 planes are oppositely aligned. So, this immediately tells us that based on the type of magnetic ordering, we can get totally different point and space group patterns in the case of magnetic diffraction. The magnetic space groups are known as Shubnikov groups and they are governed by the spin ordering. Now, we talked about anti-ferromagnetism when the moments of the ions in the two sublattices are exactly equal and opposite, so cancel each other. There are also situations when the moments of the ions are not the same, they are opposite but not equal, in which case the magnetization will not be 0, it is not completely cancelling each other, and therefore, in the ordered state there is a net magnetization which is non-zero. So, there is a net non-zero magnetization in the ordered state. So, that is known as ferrimagnetism. Here it is a Fe2 plus ion and this is an Fe3 plus ion. So, even though iron is the basic magnetic entity, it contains iron in two different valence states 3 plus and 2 plus, which correspond to different magnetic moments. So, when these iron ions Fe3 plus and Fe2 plus are aligned antiferromagnetically, you get a net uncompensated magnetization below the ordering temperature in this case. So, that is why ferrites have what is known as a spinel structure of magnetite, and these have very interesting magnetic properties and applications. Now, in addition to ferrites, these are known as ferrites. This member is typically known as magnetite. It is one of the oldest known magnetic compound. It was known as lodestone in ancient times. So, in addition to ferrite, you also have what are known as garnets, in which the sublattices are not just 2 in number, but there are 3 sublattices with anti-parallel alignment. And because of the odd number of sublattices, again there is no cancellation, exact cancellation, and therefore, they also behave like ferrimagnets. In addition to ferro, antiferro and ferrimagnetism, we can also have other kinds of magnetic ordering patterns like helical magnetism, which has been discovered by neutron diffraction studies. So, the magnetic ordering mechanisms provide a rich variety of phenomena and materials. We now turn to another important characteristic of a ferromagnet, which is magnetic hysteresis. That is a very important characteristic of a ferromagnet. Now, this is based on the so called magnetization versus field plot, and starting from the origin you go to a point where up to it getting magnetized and then come here like this and then goes back. So, this is the magnetization pattern. The arrow here shows the direction in which the magnetizing current and the magnetizing field goes. So, you start magnetizing the specimen up to a particular value of the applied field and then decrease the applied field gradually till you reach 0 magnetization, before that through 0 field, and then this is the 0 magnetization point, and then you go in the negative, in the equal but opposite direction, you go up to this point and then you come back, increase it again, goes through again a 0 field from negative values and then a 0 magnetization, and then it goes back to the original. So, that is known as a hysteresis loop. In which an initially unmagnetized specimen is taken through, an field is applied and then it is magnetized, and then it is demagnetized by reducing the field and making the field 0, and then it is remagnetized in the opposite direction, and then again the field is increased through 0 value to positive values till the original state is reached. So, that describes the complete hysteresis loop. Now, this area of this hysteresis loop gives an idea of the energy dissipation when a ferromagnetic material is used. For example, in a transformer core, in order to concentrate the magnetic flux. So, or when using a ferromagnet to produce a magnetic field, you pass a current and then you get an electromagnet in which a magnetic field is produced. So, in all these cases, the energy needed or stored in the ferromagnet is given by the area of this hysteresis loop. Now, the field, the magnetization, when you come back from 0 to 0 field from a positive value, it is seen that the magnetization does not become 0. There is a remnant magnetization. In 0 field, and then when you reduce, you need to have a field in the opposite direction which demagnetizes and makes this remnant magnetization 0. So, you coerce the field, you need a coercive field, this is known as the coercive field, which coerces the magnetization, the remnant magnetization to become 0 again. So, these are two important characteristics, the point at which the magnetic field is 0 and then the remnant magnetization is there, and the point at which the remnant magnetization is cancelled by a coercive field. So, these two values together determine the area of the hysteresis loop. So, for example, if you have an electromagnet, we want a soft iron core for which the BH loop or MH loop has a small area and it has a relatively small remnant magnetization after demagnetization, and that can be removed by a relatively small coercive field. So, the loop will look narrow, somewhat like this. So, that is how it will look for a soft iron used in electromagnets, because you would like the field to become 0 as soon as possible. You would not want, one would not want a large remnant magnetization to stay, and this remnant magnetization is removed by the application of an extremely small magnetic field in the opposite direction. On the other hand, if we want a permanent magnet, this is used in an electromagnet. The hysteresis loop has a very small area, whereas if you have a permanent magnet, if you would like to use a ferromagnet to construct a permanent magnet, you want a high remnant field which can be removed only by a large coercive force. So, that would be the nature of the hysteresis loop for a permanent magnet. So, you can see that the area of the BH loop or MH loop is correspondingly large. Now, how do you produce such a high remnant field? And this is achieved by precipitating impurities like carbon atoms, which impede the motion of the so called magnetic domains. The behavior of a ferromagnet or any ordered magnetic solid is such that there are domains inside, in which, for example, in a ferromagnet there is parallel alignment of the spins. And then there is another neighboring magnetic domain in which this may be completely different, but still parallel. So, these two within a domain the alignment is parallel, but in neighboring domains the alignment is not necessarily parallel. So, on the whole you have a large number of magnetic domains within which there is ferromagnetic parallel spin alignment, but between which there is no correlation. So, on the whole there is a complete random distribution of these magnetic domains. For example, a third domain here. So, they are all aligned in a completely random fashion, and therefore giving rise to a net zero magnetization, even though within a domain there is ferromagnetic alignment. Now, when you apply a magnetic field, these domains are all reoriented parallel to each other, producing a net magnetization. And now, in a permanent magnet material, the remnant magnetization exists because these domains are prevented from relaxing back to this random configuration by the inclusion of precipitates such as carbon. So, if you have carbon steel, for example, it is a very good permanent magnet material. Let us now discuss the ground state of a Heisenberg ferromagnet in some detail. We now know what is a Heisenberg ferromagnet. A Heisenberg ferromagnet has neighboring spins lined up parallel, and now in a given ferromagnet which consists of a very large number 10 to the power 23 or so number of spins, all of them lined up parallel in ideally. So, you have a large number of them, n spins. So, this is a product, the wave function of this state is the product of the individual parallel spin functions. So, you have something like this, the total wave function is of this kind up to n. So, all of them are up spins. Now, this state will have an eigenvalue determined by the Hamiltonian minus 2jij si dot sj, that is the Hamiltonian. So, the energy is minus 2j, assuming that the jij for all n spins between any pair of spins is the same and has the value j, and therefore n times s, where n is the number of spins. So, that will be the ground state energy. When all the n spins are lined up parallel to each other. Now, how do you know what is the nature of the excitation spectrum? Now, we can create a low lying excited state by flipping one of these spins. So, that is the easiest things to do. I can flip this spin anti-parallel and while keeping all the others the same. That would be a typical situation. This flipping can be here or it can be here, or it can be any of these combinations any one of the n spins can be tipped anti-parallel. So, all these are equivalent in which any one spin is tipped down. So, all these are energetically equivalent. So, they are degenerate. So, the wave function is a typical wave function is of this form, where the spin is can be anywhere in any one of the j sites, where j runs from 1 to n. But this will not be very easily. You can see that using this Hamiltonian on such a wave function, you can show that this is not an eigenstate. Of the Hamiltonian, Heisenberg Hamiltonian. So, we have to construct an eigenstate. How do we construct? By superposing all these various possibilities. So, with a special part. So, the real superposition where they are of the form 1 by root n for normalization, sigma e to the power I k dot r, k dot r j, psi I j, where psi I j is any one of them. This can be shown, such a superposition can be shown to have an eigenstate, to be an eigenstate, because we can rewrite this as minus 2j siz sjz plus si plus si minus plus si minus Si plus by 2. So, we can rewrite like this and show that the eigen value of energy for such a state, for this excited state, is it lies above the ground state by a value minus 2j sine square. In the long wavelength limit, sine square k a is approximately equal to k a square. So, in the long, delta E is j sine square k a, and therefore, since k is 2 pi by lambda, the wave number, in the long wavelength limit, if lambda is very long, k tends to 0. So, in the limit k tends to 0, sine square k a is just k a square or equal to a square k square. Therefore, the energy difference between the ground state and first excited state of a Heisenberg ferromagnet becomes d k square. So, d is known as the spin wave stiffness. And this gives you h cross omega. So, the omega versus k relationship is a quadratic function. Omega is a quadratic function of k. So, this is the dispersion relationship. We have already seen how phonons have a linear dispersion relationship in the long wavelength element, that is at the center of the Brillouin zone. Now, we have spin wave dispersion equation in which the omega is a quadratic function, not a linear function. So, we have a quadratic dispersion relation for the ferromagnetic excitations. These excitations are known as called Magnons. They are known as Magnons, and this is known as the Magnon dispersion relationship. Like phonons, Magnons are the elementary excitations which describe the spin wave modes which have a wave function of this form given here. So, these are just the normal modes of the propagation of the so called spin deviation. In this case, the spin deviates by flipping one spin. So, it becomes less by 1, it is s minus 1. So, the spin deviation is 1. So, it is the spin deviation which propagates through this crystal lattice because of the flipping of the various spins. So, this is a low lying excitation whose excitation spectrum is given by this. How do we know that such an excitation spectrum is there? We know it by measuring the magnetization. So, suppose we have a Heisenberg ferromagnet and we raise its temperature above 0 K. At absolute 0, all spins are lined up parallel and the ferromagnet is in its ground state, which we take as the 0 of energy. Now, we slowly warm up the Heisenberg ferromagnet above 0 K, and then we get a magnetization which is a function of temperature, and this is describable in terms of m0 times 1 minus n of k times g mu b, where n of k is the number of magnons of wave vector k. So, this is the 0 temperature magnetization corresponding to all spins lying parallel, and then out of this magnetization the number, if there are n number of excitations, each corresponding to a spin deviation of 1 corresponding to a magnetic moment g mu b. Therefore, the average value of n of k, it is the statistical average times g mu b, gives you the magnetic moment which will be decreased from the ground state magnetization because of the excitation of n spins from the ground state into the excited state with a spin deviation of 1. And we can use the Magnons like phonons obey Bose-Einstein statistics, and so their number can be determined in exactly the same way as we did for the phonons, and therefore, this can be calculated and one can find easily that this m magnetization constant times t to the power 3 by 2. So, this means that the temperature dependence of the magnetization at any temperature T is given by a relationship of this form. So, the magnetization follows a T to the power 3 by 2 dependence in temperature. In the same way, we can also calculate the magnetic specific heat. So, the magnetic specific heat also has a similar T to the power 3 by 2. It can be calculated using the same kind of statistical approach. So, if we can separate it from the phonon specific heat, the phonon specific heat, if we recall, is given by the d by t cube law at low temperature. So, this goes as t cube while this goes as t to the power 3 by 2. So, you have two terms C total is C magnetic plus C phonon for a ferromagnetic insulator which behaves like a Heisenberg ferromagnet, and this has two terms, one A t to the power 3 by 2 plus another term which is B t cube. So, we can separate out these by taking C by t to the power 3 by 2 is A plus B t to the power 3 by 2. So, if we plot the total specific heat divided by t to the power 3 by 2 versus t to the power 3 by 2, we get a straight line. So, that is the signature of a Heisenberg ferromagnet. In the same way, we can make similar calculations for an antiferromagnet and so on. I would not like to go into these details, but there are many such methods by which you can experimentally determine the nature of the dispersion relationship and hence the nature of the temperature dependence which follows from it.